Okay, hi everyone. I'm going to record this video for just the material to help you review for the cumulative final exam since the midterm exam got canceled. So I'm just going to talk about essentially overarching principles of Organic Chem 1 Lab, and I will talk about recrystallization in this video. So essentially, you're taking Organic Chem 1 Lab. Interesting thing is you guys have two basic principles of this class essentially. So I'll just drag this over here. Okay, so essentially you can divide a class into two parts. The first half, which you guys are probably familiar with, are the separation and purification techniques that you learn, such as recrystallization, selected recrystallization, and then the melting points that you did in experiments 1 and 2, extractions. Experiment 3, you guys also do distillation in experiment 6, experiment 4 TLC, then there chromatography. So you do different types of chromatography, and then experiment 5 you do column chromatography, and experiment 7 and 11 you use GC, which is gas chromatography. So these are separation techniques, and you can combine them sometimes with reactions to determine how pure whatever product you get, to quantify how pure your product is, and that's how you would probably use it in Organic 2 Lab when you do more reactions. So essentially this is experiments 1 through 7, and probably experiment 11 since you are analyzing, you guys analyze your reflux mixture from experiment 10. The second part of the second half of the lab deals more with reactions. So essentially these are the experiments that I did not list. So experiments 8 through 10. You guys do the free radical halogenation reaction, nucleophilic substitution reactions, and you guys also do elimination reactions with your reflux. So the goal of this video and the videos is I'll just focus on the first part, the first bullet that I have. So separation and purification techniques. I am going to, this is my first time making a video, so I might be kind of slow. So essentially in experiment 1, I believe you did recrystallization of an impure solid. And you guys also took the melting point of your impure solid and your pure product, recrystallized product. So essentially, what is recrystallization? That would be important to define. So essentially, you can treat recrystallization as you're taking something that's impure, which is whatever you started with, the crude product that you started with, and you're making it pure, something that is more pure. And because in this process, this means you lose, basically you want to lose impurities. You have to always remember that you will not get 100% recovery. It's not 100%. So this is probably something that you would want to remember, that even though your purity, so essentially, even if the purity goes up, the recovery essentially goes down. And so it's like kind of it's basically a give or take analysis between recovery and purity. Okay, so the first part of your experiment, you did part A, which was essentially you determine the best solvent for recrystallization. Okay, so this is an important concept to know. So what determines a really good recrystallization solvent? You have to look at the compounds that you have in question, which I have right here. So essentially you had 4 compounds. You guys had acetanilide, you had benzyl here, and then you have benzoic acid, and you also had, I will make this a little bigger, you guys had p-toluic acid. Essentially, this brings us to another question. So in any purification or separation technique, you want to make sure you know what your base is of, what is the basis of separation. So the 2 things you want to ask in any experiment that you guys did while you study is what's the objective of the experiment, and at least for first parts, not the reaction parts, what is the basis of separation. So in this case, you can probably say polarity. Polarity is the basis, and you determine polarity from functional groups. So essentially, here you all see like the benzene, you see the aromatic rings. You guys can see this is like a carboxylic acid, and this one's going to be a little, p-toluic acid will be a little less polar than benzoic because it has an extra methyl group. Benzyl has 2 carbonyls, you can see, these are ketones. One thing to note about benzyl is make sure to not say it's nonpolar, completely nonpolar, because of, I see this happen sometimes, but people say there's a dipole, and they think like the trans version and the cis version are different. They aren't, because there's a single bond, so it rotates about the single bond. So just be sure to not say anything about dipoles. Here we have an amide group. You can see there's carbonyl that's basically attached to an amine. And then you see the carboxylic acid here, which is very polar. And you can use dielectric constants that are given in the lab manual to determine these. For instance, it's given about dielectric constants that are smaller, so like around values of 2 to 3 are more nonpolar, and then values of greater than 10 are more polar. So basically, you have a like increase in dielectric constant equals more polar. There we go. Okay, and then the second part of this experiment, or it's the second part of the basis of separation, is here you want to know your solubility. So essentially, what is a great recrystallization solvent? For this case, also another one you might say, along with solubility, similar to solubility, is maybe boiling points. But that's something you can take into consideration. Boiling points, freezing points, whatever. Essentially, solubility over different temperature gradients. So basically, you want a solvent. So your ideal solvent would be something that has is insoluble at low temperatures. So basically room temperature or like 0 degrees. I wonder why is okay. So like 0 degrees Celsius, something like just cold, or room temperature or cold. And then you want it soluble at high temperatures. So hot, basically hot. So you want basically higher solubility, high temperatures, low solubility at low temperatures. So that's how you can dissolve things at the high temperatures. You can dissolve whatever analyte, so whatever you're looking at, compound, you want to dissolve that at high temperatures, and the impurities would be insoluble at high temperatures, and then you can recrystallize it back, like, so you can just precipitate it out at cold temperatures. So that's what you guys did in your experiment. Essentially, okay, that's a bad drawing. Okay, so essentially you guys had a little Erlenmeyer flask or beaker, whatever you guys use. You took a little bit of your compound and you guys put it into your flask, and then you guys want to use a minimum amount of solvent. So the minimum amount is really important because you don't want to use too much. If you use too much, you're not going to get anything out of it because of solubilities. So essentially you want to limit the amount of solvent that you have. So in our case, we said around 8 to 10 milliliters was pretty good. So then you took whatever solvent that you determined was best. So going back to that, because I didn't answer that, essentially we determined that for p-toluic acid, for the benzoic acid, and for the acetanilide, for these three things, water was the best solvent, and you determined ethanol is the best solvent for benzyl. How you determine this is you do not want a perfect match. You never want a perfect match in polarity. So the polarity cannot match between whatever solvent and solute that you use. So essentially I just call it a one-up rule. You wanna find the polarity of your analyte. I will just erase these. So essentially, you will go look at, for instance, let's say we use benzoic acid. You have a carboxylic acid here. Carboxylic acid is very, very poor. It's probably the most poor functional group that you learned of. So essentially you have a carboxylic acid here, and you guys had 4 recrystallization solvents. You had ethanol, you had, so it looks like this, you had water, you had acetone, and you had hexane. Never choose hexane because it's non-polar and you always need some degree of polarity to do anything. So don't ever choose hexane. With the acetone, it looks like that. It's a carbonyl, it's a ketone, simple ketone, and so essentially you kind of match it up. I would say the polarity of carboxylic acid is probably similar to like the ethanol, and so you know carboxylic acid is the most polar, so you have to go with the most polar solvent, which is water in this case. In the case of, let's say we were using benzyl. Why is it ethanol? So this is a ketone. It kind of matches the polarity of acetone. It looks similar because they're both ketones. So I'm going to go one up and I will use ethanol because we don't want a perfect match in polarity, so you don't want to use acetone. So you use ethanol for benzyl. With acetanilide, that's an amide. Amides are pretty poor, so people might be like, why do you not use ethanol? You can determine it as water because amides are pretty poor as well. They're less poor than carboxylic acids, but okay. So the next part, essentially you guys did that. You guys added it in, and then you guys put it on a hot plate. You guys wanted to stir it, stir fry. You guys basically set it to near boiling. You don't want to boil it out, or else everything will evaporate and you'll lose stuff. So essentially, this is hot temperatures. Everything should be dissolved in hot temperatures. So after bringing it to near boiling, if you see anything that's not dissolved, this relates more to your experiment 2, which was the selective recrystallization of benzyl and benzoic acid. So for instance, if you guys did benzoic acid, then you guys had to do hot gravity filtration because benzyl is insoluble at high temperatures. And so you would see benzyl insolubles, and basically what you would do is you take this and then you pour it. It's just like a pasta strainer kind of thing. So vacuum filtration. You guys will do vacuum filtration, which you guys use the powder funnel. So it kind of looks, it looked kind of like this. And then you guys stuck a filter paper, and then so your compound of interest was dissolved, so it went through, got filtered through, and then all this stuff is impurities. So your impurities were insoluble. And then once you had these purities that were dissolved, you then put in an ice bath. Okay, ice is not green, but basically you stuck it in an ice bath, and you also put some of your recrystallization solvent to cool it down, and then it should have became solid, and you should get crystal formation. If you guys didn't, you scratch the bottom of the flask, or you use a neighbor's like seed solution. And it just provides a lattice. Like if you have a seed crystal, it just provides a network for which it can crystallize. Once you have this recrystallized, you can technically evaporate it for over a week, but to make this process faster, I'm sorry if I call this vacuum filtration. I meant hot gravity filtration here. I don't know what I called it before, but basically you will evaporate it, and here you will use vacuum filtration. So essentially, you guys use a Buchner funnel. Oh man, don't know why it does that. So here's an adapter. Essentially, you guys use a little filter paper here, and then you would pour this through after you set it up. Let me just move this down. So essentially, you have a filter. I hate how this does this. You have a filter flask, and essentially it's connected to the vacuum nozzle. Actually this way. There we go. So air just flows through, and you're pouring through the solvent just to so it basically dries. It will just dry out your solid of interest, which is above the filter flask, more quickly, and you have residue impurities that are dissolved. impurities are dissolved in this case. The other case, impurities were not dissolved and insoluble. So that's the main difference. They're kind of opposites, vacuum filtration and high gravity filtration. And then once you have that, essentially you got your recrystallized solvent, and then you weighed it, and then you guys did mixed melting point analysis. So just to wrap things up here, I would just say, so vacuum filtration is for when vacuum filtration, you use it for remove impurities that are soluble. Hot gravity filtration is the opposite. You remove impurities that are insoluble. And another thing that's important to note is the vacuum filtration is done at cool temperatures, or room temperatures and lower, so basically cold. And hot gravity filtration is done at hot temperatures. Going back to your post-lab questions, something that might be important to take note of is when you have calculations like question 3. I mean, all these questions would be good to review, but questions like 1 and 3 would be pretty important to note. Question 2 is a nice question as well. You always want to consider acid-base reactions in all of these. Essentially, I'll explain that more in experiment 3. So for this one, you have salicylic acid, which is an aspirin. You have solubilities at cool temperatures, and you have solubilities at hot temperatures. This is a very common question that might be asked. So you want to definitely review how to do these calculations. So that would be very important to note. I know this is kind of messy. Okay, and then I will talk a little bit about the melting points. So you guys did mixed melting point analysis in experiment 2. Essentially, so for mixed melting point analysis, or just any type of melting point, it doesn't really matter here. You guys know that the MP, the melting point, should be a range, so you'll probably report it usually as a range. And your range would be very small, so I would say probably 1 to 3 degrees Celsius or 1 to 2 degrees Celsius. I won't explain how you use a melting point station or melt station in this video, but basically you want a small range if it's pure. That's probably what you'll see on PubChem or something. And then you'll have a fixed temperature for the melting point. So for instance, maybe something's melting point is like 69 degrees Celsius. This is just an arbitrary value. When you mix, so this is for your pure. So when you mix, you can also find, one more thing is you can find literature melting points, PubChem, Sigma, Aldrich, whatever, online. So like, also you should take note of the literature workshop, because that material can also be on the exam potentially. So you should know how to do literature searches. So you can compare the pure basically a pure melting point should be equivalent to the literature melting point. So you would, in ideal cases, your recrystallized, it won't be 100% pure, but it should be close to your literature melting point. But sometimes we don't use the literature one, so you can compare it to your impure or crude solid MP. And your impure crude one has impurities, and impurities they kind of disrupt the, basically they're like disruptions. If you thought of like a crystal or something, they cause some disruptions in the network, which that shouldn't really matter that much. Essentially, you would expect a smaller range. So this range, or I mean, sorry, larger range for that reason of larger melting point range. So it might be like 8 degrees, 10 degrees, something much larger than 1 to 3 degrees. And then you also expect the melting point to be lower because it requires less energy or lower temperature to, if you think of solids, and you can think of it kind of like solids and networks or something like that, it would take less energy. If this isn't really perfect and has disruptions, it takes less energy to disrupt this and make it melted into a liquid form. So it's just a lower melting point if it's impure. Yep. Let me see if there's anything else. Yeah, so basically, impure solids just, if you think of a crystalline structure, it basically causes disruptions between your pure molecules, and then it will make your solid more unstable. And so that's why you have a lower melting point, because you have a weaker structure. And then mixed melting point analysis, you can determine, so let's say you have, you guys did it with malic acid and urea and other compounds, but essentially, let's just keep it a simple example. Let's say we have this green solid and the red one. So this is, you know, these are pure. So the unknowns are all pure. So like, don't assume they're not pure and impure. They're all pure. You're given that. You just don't know the identity of them. Let's say you knew what they were and then like lost the identification. So let's say we have another compound and then we don't know what it is. Essentially, what we need to do is we mix this one. I know they're different colors, but I mean, it will be one of the two. We know that it's one of the two. So we'll mix the green one and the red one. These colors are arbitrary, or not actually these colors. So you'll mix the two and put a little bit into a melting capillary. So like something like that. You'll just put a little bit in. And then when you see the melting point, you will know. So then you get the melting points. Okay, so this, maybe I didn't make this clear, but this is your unknown. So if you had any other unknowns you were testing, you know they are pure. So we know this one's one of the two in this case. So let's say this is A, this is B. So we're asking, is it A or is it B? So A and B are knowns. they're knowns. I'm sorry if I say anything and it's confusing. So A, let's say A had a melting point of like 69.7. Let's say B, let's say it was like that to like 70.2, I don't know. And then for B, it's a melting point of like maybe like 67.8 to 70.1, or let's just say that's kind of big. Let's say it's like 69.3. So you don't really know which one it is. So you can take the unknown melting point as a pure substance, and then you find whatever the melting point is. Let's say I'm making up all these numbers. So let's say it's like 69 point. I don't know. Let's say 69.5. I don't know. It doesn't really matter in this case. Essentially, if you mix compound A and the unknown, and if the unknown is A, that shouldn't impact what the temperature is. But if it's not A, then you know the temperature of the mixture is going to be lower, and it's going to be a wider range, so it will probably be more than 3 degrees of a range. And then if it were B, same thing. Or if it were not B, then it would be lower and greater than 3 degrees. So, sorry if I just said if it were A. I mean, if it's not A. If it were A, okay, so this gets a little confusing. So basically, if this compound were A, the mixed melting point, so right here, let's say like this one was lower, and we had like a 6 degree range, and then let's say this one was around like 69.0 or something like that, well, these should all be ranges, so let's say it was like 67.6 to 69 degrees. And they should be small ranges. Then this one, and it was still around like 2 degrees. That's around 2 degrees Celsius of a range. So then you would know it's this compound, not this one, because this one has a large range. And it also has a lower melting point. So let's say if it was like, for some reason it became 65 degrees to like 67. That's much lower than this. So you know it's not A, and you know it's B in that case. Yeah, so one more thing that you probably should know how to do is percent yield. So that's the same thing pretty much as recovery. Oh man. Okay, so basically you should know how to do percent recovery calculations. So it's the mass of the initial so it's just wait a sec. So your crude amount, let me erase this. Okay, so you want your recrystallized amount because you know it's going to be less than the initial amount over initial times 100% gives you your yield. And then another calculation is the one I was talking about here with the solubilities. In cold temperature, and hot. So if you're given the solubility and a cold temperature and hot temperature, you can assume cold is like 0 degrees and hot is 100 degrees, something like that. If you're using water as a solvent. So you need to know how to do this calculation to determine the maximum possible yield of a recrystallization. So assuming everything was like perfectly done, you still have the loss, as I said earlier, because of your losing impurities. So you would use the cold solubility, and you know that you are removing impurities that are soluble in the cold temperatures. So anything that's, you use the solubility here, so anything that is soluble is the amount, the maximum amount that gets transferred from here to here. And through the hot gravity filtration. So let's say you had solubility of like 6 grams per 100 like milliliters or something, and here you use, let's say you had 8 grams, you masked out originally, and then you know 6 grams is soluble at high temperatures of, let's say something like benzyl. You use, not benzyl, let's say benzoic acid in 100 milliliters. You use this solubility, and let's say, for instance, you had, you were using 100 milliliters, I don't know. If you were using a different amount, actually that might, let's just say, to make this simpler, let's say it was like 10 milliliters. So then you know 6 grams is soluble here, and it will transfer to the next step, and 2 grams were insoluble, so it would not, it would not continue to the next part. So you have 6 grams, and then you would use the solubility at cold temperatures. I know this is unrealistic of a solubility, but just for the purpose to explain this. And then let's say it was like 0.1 grams in the 10 milliliters or something like that at cold temperatures. You know the amount soluble is going to be lost as impurity, and so you're going to take the 0.1 and subtract it off the 6 grams that you transferred here, essentially, and then you should get 5.9 grams. Yeah. Yeah, okay. So, you might have to do unit conversions to convert the solubility in terms of amount that you are using of your solvent. Otherwise, the calculations would be the same. Okay. Okay, so hopefully that was helpful. And then here's the whole board. So that was essentially your main goals of experiment 1 and experiment 2. So just remember the first part of what's a good recrystallization solvent, what's the basis of separation. In the mixed melting point analysis, it's melting points. Different melting points are a basis of separation. So you want to ask yourself these questions whenever you do any of these separation and purification processes. Okay.